Okay, good afternoon. I will collect your questions at the end of the presentation or in the break. Please take notes regarding with the slides where you may have questions. Today, we are going to study signal detection, a detector design actually, which is based on match filter. And then we'll be discussing radar clutter in space, in volume or surface clutter. Finally, we'll conclude with constant false alarm rate radar. Okay, let's start with the simple model. We use this in the cars that you took, communication systems, E316, where we model noise and signal and how to write a received signal, noisy received signal. On the left-hand side, you see a voltage signal, a rectangular pulse. This is an illustration, simple, the simplest signal model. You may simply consider this as radar pulse, and it repeats itself at every TP. Okay. Its duration is tau. It has a voltage value, A, let's say, so its power, peak power is A squared, proportional to A squared. And we got noise, as usual, due to the electronic circuitry that we used at the receiver or in the system. And usually we have a superimposed a noise superimposed on the signal, so the received signal look like this. So you have a rectangular pulse here, a noisy rectangular pulse, you see, and the goal of the detector is to extract these pulses, whether there is a pulse here or not. Then we have to consider the signal power as well as noise power. So we come to the ratio, SNR, signal power to noise power ratio. So we'd like to detect this signal at the lowest possible signal to noise ratio. The equivalent model of this is shown on the right-hand side. We got the transmitted signal. So this is the transmitted signal from the radar transmitting antenna. And we got noise in the channel or the receiver, which is superimposed on this transmitted signal. And we got the received signal right here. That's sum of the transmitted signal and noise generated. So here is the model that we used in previous slide. Now we'd like to design this part, okay? We'd like to study this part. Here you see we model the receiver as a filter, linear time invariant filter, whose impulse response is h of t. And a sampling process follows this LTI filter and takes samples at every TM. Okay, at the output of the filter, we assume that we got a filtered signal and the noise. Okay, now about the noise, this is usually modeled as white noise, which means that the power of the noise is constant over the frequency. So whatever the frequency we have the operating frequency, we always get the same power, noise power. Then that's called white noise. Here, white refers to the fact that the noise has equal power over all frequencies, typically from 0 hertz to some 10 to the 15 hertz, which covers radar operational bands. Now, we'd like to design an H of T, so a filter whose impulse response is H of T, such that the SNR at the output of the filter be maximum. Okay, be maximum. So we can write then SNR at the output of the filter, let's say S0 of Tm magnitude squared divided by the expected value of the average, expected value of the noise power. So we'd like to maximize this. And you might remember this from communication systems course. This simply goes to match filter. Now here we do not derive it. You can either go back to the course EE316 or simply have a look at the Skolnick's book where the match filter impulse response is derived. So what is it? So here is the optimum filter, which is simply matched filter. Its transfer function, by the way, let's simply remember signal concept. We got the filter whose impulse response is H of T. We got an input signal X of T, an output signal Y of T. And this output is simply X of T convolution H of T. Okay, in frequency domain, this corresponds to transfer function, and the input is X of F, and the output is Y of F. Okay, and Y of F is simply X of F times H of F. We talk about random processes. If there is a randomness at the received signal, then we can write power spectral density. So then the input power spectral density will be S of X F, and the output power spectral density is Sy of F, and Sy of F is equal to Sx of F times magnitude squared of the transfer function of the filter. So just keep this in mind. We are playing with this in the slides. Now, the transfer function of the optimum filter that maximizes the output SNR is given in terms of the input signal. So once we know the transmitted signal, then we can design a match filter for that transmitted signal. And you see that it has a constant G times the complex conjugate of the transmitted signal times an exponential function with the sampling time Tm. Okay, if we take inverse Fourier transformation of this, we see that the impulse response is simply the shifted version, delayed version, inversely delayed version of the transmitted signal times a constant G. Okay, now we then simply design a filter whose impulse response is H of T. It's matched to S of T. That's why we call as it match filter. So this filter is matched to S of T. Then to design a match filter, we have to have a signal first. We have to define a signal. the transmitted signal should be known, should be given, so that I can design a match filter for that transmitted signal. As an illustration, at the bottom, we can see an arbitrary signal here, whose duration is Tm, okay? And it's an arbitrary signal. So its match filter should have an impulse response, which is simply the mirror image of the signal, okay? So you see, this is mirror image of the signal. Additionally, there is going to be a delay by Tm. It's not shown in here, but just the reverse of this. Okay, so suppose that we got this h of t here. Okay, h of t is here. I know x of t. Then I can determine y of t. How? We simply convolve input and the impulse response. So in next stage, we see how to implement convolution. Here we see a sinusoidal pulse. Okay, so here is a sinusoid whose amplitude is h. So just like a radar pulse, simply. We have studied this in the laboratory and in previous lessons frequently. So you are familiar with this signal. There's going to be a carrier frequency, a duration tau, okay, and it repeats itself. So we take a single pulse in here. So it's the match filter impulse response for this signal will be just the signal itself, which is shifted by Tm and mirror imaged version. And convolution, as you might remember from signals and systems, is simply a sweeping operation. If we try to visualize this, we just take the input signal and then sweep it from minus infinity to plus infinity by the amount, which is simply denoted by tau. So every new tau value, we look at the input signal and the impulse response of the filter and determine the overlapping area and then getting the output signal. This is a simple integration, as you can see here. We can do this in discrete form as a summation. And if we got a radar pulse like this, this sweeping will give us a sinusoid whose envelope follows a triangular waveform. Okay, but note that the duration here was Tm. Now the duration becomes twice the duration of the pulse, which means that if I transmit a signal, a pulse of duration tau, then the output of the filter will be 2 tau. So my decision simply is delayed by tau. This is discussed in radar signal processing concepts. This is not the subject of this course, actually. So let's see how to implement this convolution. Just an example, you may refer to the course, communication systems and signals and systems, where you can see the details of convolution in either discrete form or continuous form, so in summation or integration. Here we are given a sequence, h of n. This is impulse response of the filter, and we got an input signal, x of n. So we just take the mirror image of h, right, n minus m, which is just reverse of this, as you see, and then sweep this three samples, three values of the sequence to the right, one by one. At the first stage, there is 1 and 1 here. So 1 times 1 is 1. Next, it's going to be 1, 2, 3. Then that's going to be 1 times 2, 2, 2 times 1, 2, 2 plus 2, 4. Next, we got 1, 2, 3. Then it's going to be 3 times 1, 3, 2 times 2, 4, 2 times, so 3 times 1, 3. So 3 plus 4 becomes 10. Okay, so when we sweep this to the right, at the end, we got a sequence like this. Okay, you see the size of the output sequence is going to be the sum of the size of the two sequences minus 1. Okay, we can also illustrate this in we can illustrate a graphical process here as a graphical process for convolution, discrete convolution. Here is x of n, here is g of n, and mathematically the output is convolution of input and the impulse response. So we just implement this one, as this is discrete. We simply take x of n. Here x of n is for 0 it's 2, and for 1 it's 2 again, and for 2 it's 2 again. Okay, and this is x of n. And for g of n, it's at 0 it's 1, at 1 it's 2, and at 2 it's 3. Okay, so we then take the reverse of x of n and then sweep it to the right again and look at the numbers and add them up to get the output of the filter. As you can see, the filter response is starting from 0, 1, 2. It should continue that way, right? We have to extend this to cover all the range. Okay, so we know then how to design a filter, which is the heart of the detector. Next, we'll be looking at the waveform, what kind of waveform we can use. And for this purpose, we start with rectangular pulse, which is the basic waveform that we have been using. Let's take an S of t here, whose duration is tau, just a radar pulse. And we look at the spectrum of the signal. We see that it is a sync. So this is the magnitude. So actually this should be something like this. Okay, so here is 0 and the first null, second null, and third null goes like this. And we have already shown this, that this is 1 over tau, this is 1 over minus 1 over tau. And if there is a sinusoid here, then the spectrum will be shifted to F0, which is the frequency of the sinusoid. We have already discussed it in the first or second lesson. Now, suppose that I would like to use such a waveform, and what will happen in frequency domain, or is this the most appropriate waveform to be used in radar signals? Let's try to understand this. Once I design this signal, I choose this signal, I automatically choose the filter actually, right? Because it is given, its impulse response is given in terms of the signal. So we see that when we use a pure rectangle, we have a main lobe. We have a main lobe here, as well as many side lobes. So if we get the magnitude of this, so amplitude spectrum, we'll see side lobes in here, okay? Their amplitudes decay with the frequency, but it goes to infinity, okay? Which is a problem, because if we are interested in the range of the frequencies of the signal, so in order to recover the signal, we have to design a filter, or we have to design a receiver which covers all the frequency components in this range, which is impossible as the signal spectrum goes to infinity. Then we have to do something here. It's mostly called pulse shaping. So one way to reduce the power in this side lobes is to shape this rectangular pulse. So instead of a pure brick wall type rectangular pulse, we can smooth it just like this, okay? Which will suppress the side lobes, and the energy or power in this side lobes will be reduced, okay, based on this smoothing process, which is called pulse shaping. Sorry, this is one way to use in order to reduce the signal power in side lobes. Another way is to use a waveform whose spectrum is limited, or whose spectrum can cover a very limited frequency band, and its side lobes are quite low or can be ignored. This is exponential waveform, Gaussian waveform, whose spectrum is again a Gaussian pulse. Usually this is just like a matched signal, because we do not have side lobes, so the band is quite well defined. And once we use this waveform, we can easily design a match filter. So between this rectangular pulse and this exponential pulse, there may be many different alternatives, many different pulse shaping methods, or many different waveforms that we can choose, and then we can design a match filter accordingly. Here is a table from the textbook showing the efficiency of non-matched filters compared with matched filters. Here we got a rectangular pulse at the input, and we use a third order Bessel filter, for example. Okay, and we see the loss in SNR. How much loss do we have in SNR when we use a third order Bessel filter? Again, please refer to the previous slide where we got the rectangular pulse and we got side lobes. So we eliminate side lobes, which means that we have a loss in SNR. We use quadruple tuned or Butterworth filter, double tuned Butterworth filter, 5 cascaded single tuned stage, and goes like this. And at the bottom, we see Gaussian pulse, which is the pulse that we have talked about in previous slide. As you see, once the signal is Gaussian, its match filter will be Gaussian too. This is good, which means that there is no loss in SNR. So that's simply matched filter. On the left-hand side, you see how we implement match filter. We have already shown this in previous slides. Remember, a rectangular pulse, modulated sinusoid, whose frequency is f0, and the match filter of this input signal will be simply a rectangle, right? Its envelope is a rectangle, and for a rectangular pulse, we got a sinc function. I mean, in spectral domain, we got the sinc function, so the match filter frequency response will be a sinc function simply. And once we convolve the match filter impulse response with the input signal, we'll get a sinusoid again, whose envelope follows a triangle. Okay? Now, in the next, then, we simply take samples from this triangle. Okay? So if there is a signal, an input signal, we got a high peak here. Okay? If we got noise only at the input, then this is going to be just a noise. Okay? So the next stage, the sampling process, will be based on taking a sample from this envelope signal and then compare it with the threshold. Okay, so simply we put a threshold here, for example, like this. And then if there is a noise at the input, we got a noise here, and the sample will be below this threshold. And then we report that, we declare that there is a noise, not an echo signal, while if the sample is above this threshold, which means that the input signal is a sinusoid, then we report that there is an echo signal. Okay, so it was about how to design a receiver. In the next lesson, the last lesson of the semester, we'll be talking about details of signal processing in the receiver of a radar system. So from now on, we'll be talking about clutter. We have already talked about clutter previously, not in detail, but we said that any echo from the objects over the link or around the target is called clutter. It might be echoes coming from an object. It might be echoes from the sea. For example, it might be echoes from clouds or birds or other objects nearby the target. And typically, we will be modeling clutter on land or sea. So surface clutter and volume clutter. And the most important thing is about how to model this clutter, actually. Before that, let's go back to the radar cell concept, because the source of the clutter is actually the objects inside the radar cell. In 3D, as you might remember from the midterm examination, there are 3 resolutions that we have described for radar systems. Range resolution, so the resolution in range, and resolution in elevation, and resolution in azimuth. Okay? Once we determine these 3 resolutions, we actually determine the radar cell. Okay? That's a volumetric, that's a volume in space. Okay? And it's highly dependent on the range and the beam width of the antenna in azimuth and elevation. So higher the range, higher the resolution. So the number as a number is higher in range when we go away from the radar. Okay, we can think about surface clutter when there is an object over, let's say, this azimuth plane, for example. If there is an object inside this three-dimensional cell, then that's going to volumetric or volume clutter. We'll be talking about in the next slides. Before that, we talk about metrics. There are two types of clutters that we'll be talking about in this slide: surface clutter echo, surface clutter, and volume clutter. And there are two parameters for that. One is clutter cross section per unit area and clutter cross section per unit volume. So in 3D and 2D clutter cross section, these are dimensions parameters, just like reflectivity. Okay, so how much reflection we get from the object, undesired object. And usually we use RCS of the object in a specific area, typically AC. We do not, it's denoted by AC, and or VC as a volume, and divide this RCS by AC to determine this clutter cross section per unit area. Similarly, eta, which is the clutter cross section per unit volume, is RCS of the clutter occupying a volume, sigma c, divided by that volume, Vc. Both are dimensionless, so just a number. If it is written in dB, it's 0 to minus infinity dB, or from 0 to 1 in number. Okay, let's see surface clutter. Here we have a radar, an air platform, which illuminates ground, and the pulse width is tau, and we know the radar range equation, simplified radar range equation for any target whose RCS is sigma meter squared, and for a target, let's say with sigma t, we can write a simple simple equation, radar range equation, and write the signal power. Okay, here S refers to signal power, which is the received power actually. Next, what will happen if we have a surface clutter then? How much signal power is received due to this length illuminated area? On azimuth, we can see this illuminated area. Okay, if there is an object here, a target here, whose radar cross section is sigma t, then we got this power. It's okay. So how about the received power due to this clutter, this surface? Okay, so it's dependent on the pulse width, the range, and the beam width of the antenna, as well as the angle that is measured from the ground to the line to the radar. Okay, and so the area from which we got clutter echo is going to be r times theta b theta over 2 secant psi. Suppose that the clutter cross section here is given as clutter cross section per unit area times AC. Then we can determine the clutter power using this formula. So we just insert this AC into here, and then this is known because this is dependent on the nature of this surface, whether that's a road, for example, if there is a forest or a farm, for example, whatever it is. So it's highly dependent on the nature of this surface, as well as the frequency, of course. And once we determine sigma c, then we can write the received power due to clutter, and it's denoted by C. So we got signal power right here and clutter power right here. So when we inspect this clutter power, we see that it's proportional to, inversely proportional to the distance cube. It was r to the power 4 in signal, as you see, target, the signal power was proportional to the inverse proportional to the r to the power 4. Now the clutter power is inversely proportional to r to the power 3. Okay, so that's a very important point. The next slide will be discussing that. Now, remember that in the beginning of this lesson, we talked about signal to noise ratio. This was undesired signal, right? Generated by the receiver. This is the echo signal we expect. So this ratio was critical. Now, when we got a clutter, then we got clutter echo signal, C, and then we talk about signal to clutter power ratio. So from the previous two equations, we can write signal power to surface clutter power ratio in terms of the reflectivity of the surface, the radar cross section of the target, as well as the range, beam width, pulse width, and the angle. Okay, and from here we can write maximum range in terms of S over C, signal power to clutter power ratio. When we minimize S over C, we maximize the range. Okay, and note that the same range equation was written previously for signal to noise ratio. Okay, and if we compare these two, S over C minimum and S over N minimum, we see that S over C minimum is proportional, inversely proportional to the maximum range, while S over noise, S over N minimum is inversely proportional to the fourth power of the range. Okay? So then there may be some conclusions that we can draw. There may be two different cases. If the clutter is a limiting factor, then we can talk about this equation. If the noise is a limiting factor, we talk about this equation. So we then make two cases, talk about two cases, clutter-dominated operation and noise-dominated operation. In clutter-dominated operation, as you can see, range appears first power instead of fourth power in here. And if we simply change the RCS by a factor of 2, the change in range by a factor of 2. Okay, if you make it 2, then that's going to be 2. While increasing TX power does not change S S over C, there is no transmitting power in this equation. So it doesn't matter you increase the transmit power or not, there is always the same signal to clutter ratio. And moreover, this S over C is independent from the antenna gain and effective aperture. So we do not have gain and effective aperture of the antenna in this equation. But beam width of the antenna is critical. So theta B here is critical. So somehow this is related to the gain, but not directly, because we may talk about two different beam widths, and the gain is dependent on the two. So for this equation, we talk about only beam width, not gain. A long pulse may decreases definitely signal to clutter's ratio, as signal to clutter ratio is inversely proportional to the pulse width. So smaller the pulse width, higher or larger the signal to clutter ratio. And signal to clutter ratio may change from pulse to pulse, and pulse integration may not work just like in SNR case. On the other hand, noise-dominated radar operation, as we know, change of RCS by a factor of 2, change in the range only a factor of 1.2. So here we got R to the power 4. Okay? And this is, you see, inversely proportional to the radar cross-section. So we take half power of 2 inversely, we get a change in the range only 1.2. It was 2 in S over C. If we increase the transmit power, we can easily increase the signal to noise ratio, because the signal power is directly proportional to the transmit power. And longer the pulse duration, higher the SNR in SNR or noise dominated radar operation. Okay, let's talk about the effect of angles in clutter echoes, on clutter echoes. Again, we consider a air platform, a radar installed on air platform, and we got Earth here. There's a curvature, and let us first describe angles here. Here is the line which is perpendicular to the surface of the Earth, and here is the line from radar to the surface, so clutter, and there is a tangential line here to the surface, and this angle is called grazing angle. So if we take Earth as a plane, then this tangential line simply the surface of the Earth. Now, there is another angle here, which is called depression angle, and measured from this line to the direction of the platform. Okay, as the Earth is not plane, then depression angle is different from grazing angle. And incidence angle is measured from this tangential, so the line, from the line to this vector perpendicular to the surface of the Earth. Okay, so the most challenging case is where the grazing angle is very small, because when the grazing angle is small, then we expect shadowing due to the objects over the surface of the Earth, and we get multiple interference. Now, in here, in this picture, we see the variation of the reflectivity, so RCS simply, scattering coefficient. So whatever we call, there are several names for that. Just use reflectivity. Reflectivity is simply you see from 0 to 90 degrees when it's shadowing and multiplet, then it is quite small and it increases until when we look at the surface from the top. So direct reflection, scattering. And in the subsequent slides, we'll be giving some RCS values for surface and sea clutter. All are simply based on measurement data, and there is no simple formula for this reflectivity. Usually, we have to conduct measurements and collect data and then analyze the data statistically and try to evaluate how reflectivity varies with the frequency and the object. In doing this, we got statistical characteristics as usual: mean value, median value, and standard deviation or variance, and RMS value. So we just repeat the measurements n times and then get the average, and then its squared will be RMS value. For standard deviation, if it is a random process, a random variable, sorry, we simply take the expectation of sigma minus mu sigma squared from the probability course 213. We have already, as you might remember, studied standard deviation and variance and how to calculate that. I'm not going into details of that. Just please remember that we got mean and standard deviation whenever we got a random variable in the clutter measurements. Okay, let's see land clutter first. There are three different grazing angles, three different cases: low grazing angle, medium grazing angle, and high grazing angle. As I said earlier, all are based on measurements, and we talk about mean value and standard deviation or variance. And there are different sites and with different features and different locations. And the operational bands will be from VHF to X. And the accuracy, RMS accuracy of the clutter echo measurements is within 2 dB. And as we couldn't remove the atmospheric attenuation, so the measured values are somehow includes atmospheric attenuation. The range in which the measurements were taken could be 1 to 50 kilometers, depending on the site. Okay, let's have a break here, and then we'll continue. Do you have any question? Okay, in the slide, we can see clutter as RCS for forest and farmland, for X band and VHF band. We can see the values of RCS from minus 70 to 0, not 0, less than 0. And the number of hits per set are shown, indicated in the vertical axis. For forest, for example, for X band, the mean value is somewhere between minus 20 to minus 30 dB. and about 99% of the data of the RCS values are within the range from minus approximately 12 dB or less. For VHF, we see that the mean value goes up to minus 10 dB, sorry, and it's rather concentrated around, you see here, around minus 40 to minus 5. For X-band, it's a little bit spread from minus 65 to minus 10. For farmland and X-band, we see that it's quite distributed from minus 80 to minus 10 dB. The mean value is somewhere about minus 20 dB, while for VHF, it's about minus 70 dB, which is quite low compared with, if I look at the center here, the concentration, it's quite low compared with X-band. Here is a table showing land clutter for low grazing angle. All are measured values, and from urban to mountains region, or desert or grassland, agricultural or forest, you see, all are listed here. From VHF until X-band, we see a variation of 10 dB from VHF to X-band when it is urban. Urban means the city centers, or around city centers. For mountains, to VHF, it's a little bit higher than urban. And for X-band, it's quite low compared with urban. So it's highly dependent on the frequency, as you see. The operational frequency then is quite critical for detecting objects in urban or mountainous areas. Here is again a measured land clutter variation, again for low grazing angle from VHF to X-band, and we got the mean values at the center you see here, and the standard deviations here, and the extreme values just appear here. So for VHF, for example, the median value of the mean clutter strength reflectivity is in between minus 45 to minus 10 approximately. In a few measurements, it's found to be minus 65, less than minus 65, and goes up to some minus 2, for example. When the frequency increases, the variation decreases, as you can see. For X-band, it's quite concentrated around the mean. So the standard deviation is quite low compared with VHF. So from this picture, from this measurement, we can conclude that the standard deviation of reflectivity is highly dependent on the frequency, and for high frequencies like X-band, S-band, it's quite low, and for VHF band, it's quite high. Okay, how about medium grazing angle? For medium grazing angle, where we talk about several tens of degrees, typically, for several tens of degrees, up to 70 degrees, right here, for example, from some, let's say, 5 degrees here, goes up to 70 degrees in these measurements. There are 3 bands, KU, X, and L. and Ku and X have a similar pattern, as you can see, with increasing grazing angle from 20 degrees. They're almost, they have similar pattern, and their values are very close to each other, and they're almost linear, linearly varying with the grazing angle. For L band, on the other hand, it's it's starting from 30 degrees, goes up to 80 degrees, and it's again linear, although its slope is different from the Ku and X band. It increases um, suddenly after 70 degrees. On the left hand side, we see the variation of the reflectivity normalized with the angle. Here we see gamma, which is reflectivity divided by the sine of the psi, the grazing angle. And it can also be written in terms of frequency, taking 10 gigahertz as the reference. And we can see how this gamma, which is function of frequency and angle, varies for cities, open woods, cultivated land, and desert. You see it's quite low for desert, high for cities, and its mean value somehow starts from minus 25, goes up to minus 10 dB. So simply these graphs are quite important for understanding of how reflectivity, so RCS of land clutter varies with frequency as well as the objects in the on the land. How about sea clutter? When we talk about sea clutter, we should first give the sea state. Sea state defines actually or measure the wave size or height, and usually waves are related to wind and the duration of the wind in time and space, as well as its equilibrium conditions are important for classification of the sea or defining the sea state. In the world, there is a there's an agreement on the sea state and the wave height, and we see from 0 to 9 sea states, and see the wave height from 0 to over 14 meters, which is just like the tsunami. And on the right hand side, you can see descriptive term for the sea. The state, sea state 0 refers to the sea where it is just like glass. How to call in Turkish, çarşaf gibi. Okay, the state is sea is çarşaf gibi, we call it. Okay, calm and glassy. And over 14 meters, we talk about just like the tsunami. In most oceans, we are talking about this region. Okay, these are very typical. Okay, how do we evaluate reflectivity of sea clutter? It's again highly dependent on the speed. And in here, in this picture, we see a measured radar cross-section of sea state where the wind speed is about 10 to 20 knots. It corresponds to sea state of 3 or less. And for different bands of the operational frequency, we can see from 50 megahertz goes up to X band, so 12 gigahertz. And we have two different polarizations here, vertical or horizontal. And the response of the sea surface against this vertical and horizontal polarization are quite different, especially at low frequencies. And we see that after 50 degrees of grazing angle, all of the operational bands have similar pattern. The RCS reflectivity actually increases almost linearly after 50 degrees, which means that we look at the surface of the sea from top. Okay, so it was about the discussion on clutter, sea, land, surface clutter. Next, we'll be talking about how to reduce the effects of this clutter. Constant false alarm rate radar. Before that, let's go back to the misdetection, false alarms, and proposed of detection concept. This was a slide that we have used in, I think, the second or third lesson. Here we got a received signal over time and the voltage, yeah, and we got a threshold where we measure the sample echo signal and compare with the threshold. If it is less than this threshold, we report that that's a noise. If it is above this threshold, it exceeds the threshold, we report that there is an echo signal. So here, for example, for point A, sample A, it's quite clear that the sample taken is greater than threshold, so we can declare an echo signal. So there is a target present. Okay, for B, it's just about threshold. We can either report this as an echo signal or a noise. If it is a real echo signal, but we report this as a noise, then that's going to be a misdetection, okay? Because there's an echo signal actually, but we report this as a noise. On C, for example, if this is a noise, but we report this as an echo signal, then this is going to be false alarm. So then the threshold here is very critical. If we fix this, and if the clutter affects the signal with time, then it's likely that we can make many errors. We can have more misdetection or false alarms. So we have to think about how to determine this threshold when we have, let's say, surface or sea clutter, where there's a dynamic environment. The clutter is varying with the time and position of the radar or motion, or the land or sea itself. So we have to make this dynamic or adaptive. So this comes to the constant false alarm rate radar, where we adaptively change the threshold according to the effects, according to the echo signals, clutter echo signals, and external noise. Okay, the idea is quite simple. We take samples many samples and then get the average. And if we see that the signal increases slowly, we increase the threshold. Otherwise, if we have a signal slowly decreasing, then we reduce the threshold. Okay, how do we implement this? We use step delay line, as we have described previously. We take more than one samples, okay, and store those samples before the detection process, and take another sequence of samples and record them, and then add the average of those samples, and then compare the average with the signal that we want to make a decision. So you can simply consider over this time axis samples, just like pulses. Okay, you got many pulses. Each pulse corresponds to a time, instant time bin. Okay, we have many here. And let's say this is my test signal. So with this signal, I will determine whether that's an echo signal or a noise. In order to make a decision regarding with this pulse, I consider all these pulses and these pulses, get their average, and then multiply by them with a k factor that I tune, and then compare that with the test cell. Okay, so if the power of these pulses increases, then I can increase the threshold. So the decision here will be highly dependent on the power of these pulses as well as the power of these pulses, which means that in space, now let's draw the space equivalent of this. Let's say this is the space, and here is my object, and here is clutter. Okay, so each pulse here corresponds to echo signal, corresponds to a to a distance here. Okay, r. Let's say here, 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 here. So here is my target, and here we got some objects, clutter. Okay, so if there are strong signal coming from this clutter, then I can increase the threshold so that the false alarm will be somehow fixed. Okay, that's the idea. So then the question is, how do we determine the number of cells in this step delay line? How many cells is the best number, or the optimal number of pulses? If we increase the number of pulses, we simply increase the sensitivity to the clutter. And if we increase the cell number, we simply increase the detectability. But if we use more pulses, then we may also have some problems about the loss. We may have a problem with the signal to noise ratio. And on this graph here, we see how CFAR loss, CFAR loss is varying with the number of reference cells. Let's say M here. But of course, the number of pulses that we would like to integrate, we can integrate, and also probability of false alarm will be important. So we see here 1, 2, 3, 4. You see, and the number of pulses integrated is 1, 3, 10, 30, and 100. And probability of false alarm goes from 10 to the minus 8 to 10 to the minus 4. And when we increase the number of reference cells for any PFA and N, we simply reduce the CFAR loss. That's good. And when we increase the number of pulses integrated, simply we can reduce the number of pulses, reference cells, okay, number of reference cells. So increasing the number of pulses integrated will be decreasing the reference cells. So there is going to be an optimization. We have to determine the probability of false alarm and the number of pulses that we can integrate, and then we can determine the reference cell number accordingly. By the way, CFAR loss is defined as SNR with CFAR divided by SNR without CFAR. Okay? So this is the case where we got simply pulse integration for any specific PFA and PD. Okay? Once we got it, we use CFAR, and then the SNR, of course, increases, and then we are looking at how the CFAR loss is dependent on the number of reference cells. Okay, this is the final slide, the last slide of this presentation, of this lesson. It's about signal management. There's an overall picture of a radar system, and we have processes. In the next, the last lesson, we'll be talking about signal processing. So this block, we actually talk about IF amplifier, which was somehow match filter. And then we got, detector and decision stage. When we inspect this picture, we see a waveform here. This is the transmitter side. And here is the receiver side. And we have an exciter, simply a waveform. In our laboratory activities, you can remember a voltage controlled oscillator, for example. And then we got a power amplifier here from the laboratory, the modular radar that we have built up in the laboratory. And then the duplexer, we did not use duplexer, of course, we used 2 antennas, okay? One for transmit, one for receive. And there are many subjects that we have to consider from the channel side: spatial filter, resolution, angle measurement, beam shaping, adaptive antennas, for example, multipath resolution, for example. These are the concepts that are dealing with the channel and antenna. At the receiver side, we got LNA, as you might remember from the laboratory, and then mixer. Right? There was a mixer that we used, and this VCO was connected to this mixer, as you might remember, using an attenuator right here to balance the power from the LNA and the VCO. And then we got a low pass filter here in laboratory. The modular radar we used in laboratory. And then we look at the output of the LPF using a spectrum analyzer. Now, in reality, of course, we got IF amplifier, detector, decision stage, and then display. So all these functions are performed automatically. Operator is expected to, to, to evaluate the outcomes, the targets on the display and make a decision or inform another unit or person. Okay, so as you can see, there are too many things regarding with a radar system. This quite complicated system. We have actually studied very basic concepts in radar systems. In practice, we have some resources, as you can see here. And the time, for example, we'd like to minimize time usually, minimize bandwidth, minimize space, and minimize energy, especially for air platforms. Space and energy are very critical, and bandwidth is critical as well. And you have to process all of this. You have to do all these processes, perform these processes in a very short time. And you have to respond very quickly. Okay? And we have many external factors, as we have discussed in previous slide: clutter, propagation aspects, and target characteristics, missile, or an air platform, or UAV, or a submarine, for example, or interference coming from other radars or systems. So in this slide, we simply reviewed signal management in radar systems. Okay, so here is a list of problems from the textbook. I would rather see your questions in the office hour regarding with this questions, problems. So I'm going to end the lesson. Please ask your questions now.